Swift is a language that is most commonly used to write apps for Apple client devices, such as iPhones. Since being released in 2014, Swift has become one of the most popular languages due to its high performance and developer ergonomics. In 2015, Swift was open-sourced, creating the opportunity for Swift to be used outside of the Apple ecosystem. If you write an iPhone app today, your frontend is in Swift, and your backend is probably in NodeJS, Java, or Ruby. Engineers are working to port Swift to the server so that the Swift developer experience is isomorphic, the same language on the backend and the frontend. Chris Bailey is an engineer at IBM working on Kitura, a Swift web framework. In this episode, we discuss the history of Swift, why it is so appealing to developers, and why Swift could become a server-side language with as much popularity as Java. Software Engineering Daily is having our third meetup on Wednesday, May 3rd at Galvanize in San Francisco. The theme of this meetup is fraud and risk in software. We'll talk about ad fraud and fraud that Coinbase faces. We will have great food, engaging speakers, and a friendly, intellectual atmosphere. To find out more, go to softwareengineeringdaily.com/meetup. Now let's get on with this episode. At Software Engineering Daily, we need to keep our metrics reliable. If a botnet started listening to all of our episodes and we had nothing to stop it, our statistics would be corrupted. We would have no way to know whether a listen came from a bot or from a real user. That's why we use Encapsula to stop attackers and improve performance. When a listener makes a request to play an episode of Software Engineering Daily, Encapsula checks that request before it reaches our servers and filters bot traffic, preventing it from ever reaching us. Botnets and DDoS attacks are not just a threat to podcasts. They can impact your application too. Encapsula can protect your API servers and your microservices from responding to unwanted requests. To try Encapsula for yourself, go to encapsula.com/sedaily and get a month of Encapsula for free. Encapsula's API gives you control over the security and performance of your application, whether you have a complex microservices architecture or a WordPress site like Software Engineering Daily. Encapsula has a global network of over 30 data centers that optimize routing and cache your content. The same network of data centers that is filtering your content for attackers is operating as a CDN and speeding up your application. To try Encapsula today, go to encapsula.com/sedaily and check it out. Thanks again, Encapsula. Chris Bailey works on Swift at IBM. Chris, welcome to Software Engineering Daily.
Thank you for having me, Jeff.
Yeah, it's great to have you. Today we're talking about Swift on the server, but I'd like to start with a discussion of Swift itself. Swift is a programming language that is most commonly used to write applications for the Apple ecosystem. Why was the Swift language created?
Swift was created by Chris Lattner, who had previously worked on LLVM, which is kind of like a platform and a toolkit for creating and running programming languages. So it has an implementation of C called Clang. And I think when he joined Apple, one of the things that was kind of clear is that to program for the Apple ecosystem, you have to use Objective-C, which has been around a long time, and I guess it's fair to say hasn't had a lot of modernization done to it. So Swift is or was, this opportunity to revamp the developer ecosystem for the Apple ecosystem and to create a new language which those developers would find easier to use and could actually provide their input to. The goals of Swift are declared that it should be fast, expressive, and safe. And basically those are the characteristics that developers really want to build their applications.
Swift came out in 2014, but the iPhone has been around for much longer than that. Before Swift, as we mentioned, iOS apps were written in Objective-C, and both Swift and Objective-C compile to the Objective-C runtime. Give an overview of the compilation paths for Swift and Objective-C.
That's actually not completely true.
Okay.
So
my Wikipediaing has failed me.
So if you're running on Linux, there is no Objective-C involved at all. So when you compile your Swift code, what you're actually creating is a native binary, so an executable or a library for that platform. Now, what it does do is it does seamless bridging with Objective-C. So if you have existing Objective-C code that you're using somewhere in the Apple ecosystem, whether it's desktop Mac or it's iOS or it's watchOS, then you can reuse that code because you can call Objective-C code and use it from your Swift code. So if you're running inside the Apple ecosystem, there's a good chance that you've got some Objective-C code running somewhere inside your application. But on Linux, there is no Objective-C runtime that's provided. So everything is native Swift code that's compiling down to native modules for that platform.
When Swift was introduced, it was described as Objective-C without the C. I think you could also describe it as having these collections of features that allow it to reach for those, what is the ideal, that you said security, speed, and what were the pillars, the pillars of Swift that you mentioned?
Safe, expressive, and fast.
Safe, expressive, fast.
Yeah, so the aim is that it's safe in that the language itself makes it harder to program with bugs. So one of those concepts is something called optionals. So one of the classic problems that you get in programming is null pointers. Now in Java, if you have a value which you've initialized, which you've created but you haven't initialized, it's going to have null as the value. And if you try and use null, so you think it's like a string, and then you try to access something from that string, you'll get a null pointer exception. If you do that in C code, so you have uninitialized values that you try to access, then that could be somewhere random in memory, and you generally end up with a crash. So Swift tries to avoid that problem. Yes, so a crash or a SIG-SEGV or a segfault, yeah. So Swift tries to avoid that problem by using optionals. And the idea is when you have a value, you can mark it as being optional, and that means it has scope to be nil. Or you can have something which is not an optional, which cannot possibly be nil. So most values are non-optional, and that means they must be initialized to something. So you know you're never going to get this null pointer exception or this SIG-SEGV trying to access the value because you know it cannot possibly be nil. Now, if you want something that could be nil, then you have to mark it as an optional. And before you convert something that is optional to something that isn't optional, then you have to do a check around it to make sure whether or not it's nil. So that means you've actually got this sense of types which you can safely access without worrying that it may or may not be nil and having to wrap everything you do in these nil checks. So that's just one of the things that they've implemented to make it easier for developers to write code which has less bugs.
We had a show recently about LLVM, and as you mentioned, the creator of Swift is Chris Lautner, who also created the LLVM. The LLVM is this ecosystem of compiler tools. How does Swift leverage LLVM? So
LLVM lets you effectively build multiple languages, and Swift is one of those. So when you're writing Swift and you compile it, it's actually using the compiler tools from LLVM to take your Swift code and convert it into the machine assembler, effectively, which is going to be executed on your platform.
In the LLVM show, much of the discussion focused around this intermediate representation, that there's a lot of work that goes into being optimized. So, that any code that compiles down to the intermediate representation language gets to take advantage of the intermediate representation optimizations. It's almost like the Java bytecode of, well, it's a more flexible platform than Java bytecode. Well, I guess you spent a lot of time in the Java ecosystem. I was looking at your background. You spent like 15 years in the Java ecosystem. How does the LLVM platform compare to the JVM?
So in a lot of ways, the concepts are the same. So when you're doing compilation, whether it's ahead of time, which is what you have with Swift, right? You write your Swift code, you compile it, you get these binaries, and that's what you execute. So there's a single upfront compile stage. When you do that, the first thing that happens is the code that you write gets parsed, and that creates, this intermediate representation language. And at that point, you can start to do the optimizations. So you can look at things like loops, and you can say, well, I know that people typically write loops such that I go around it a whole number of times and then break out only once, say, 100 iterations have been completed. So usually you go around that loop several times before you exit. So you can use that to optimize to the fast path to be to iterate around and the breakout to be the exception. And the way LLVM works, because you have this intermediate language, then it doesn't really matter what the front-end programming looks like. Once that's parsed and becomes down to the intermediate language, then those compiler optimizations can be applied regardless of what the front-end syntax looks like. So that's one of the ways in which Swift, even though it's a relatively new language, has quite a lot of compiler optimization in it because it gets to reuse what was already there in LLVM. Now, those concepts are actually very much the same in Java. The difference is Java kind of has two compilation steps. The first, you write your Java code and you run Java-C, the Java compiler, and that creates bytecodes. Now, bytecodes are just portable, right? You can pick them up and you can run them on any platform. So unlike Swift, where you compile on a platform and it generates the binaries for that platform, the output of compiling your Java code is these bytecodes in a class file, and you can pick up that class file and run it on any platform that has a JVM. Now, when you run it on the JVM, that JVM still has to get to the point that it's running assembler instructions for the machine it happens to be on. And the way Java does that is to do that compilation down to machine code at runtime. So it uses something called a JIT, a just-in-time compiler, to do that. And the concepts of just-in-time compilers are actually very much the same as they are in LLVM. It takes the bytecode and it converts that into an intermediate representation language, an IRL, and from there it applies the optimizations before compiling it down to the machine code. Now, one of the slight advantages that you get from the JVM approach of doing this at runtime is back to kind of that loop example that I gave you. A static compiler, one that compiles ahead of time, can only guess how a loop is being used, right? It's going to assume you'll go around the loop several times and then break out only once you've gone through these multiple loops around the cycle. A just-in-time compiler has the advantage that it can actually profile the way the code is being executed because it compiles at runtime. So it can see how your program is actually running, and it can say, actually, this loop's different to normal. Typically, it will not go around the loop. It will do a check, and it will break out immediately. But only in the exception case does it go around the loop several times. So it can actually optimize the reverse way to what you would typically have because it can actually watch the code and see the way it works. And that means that there's actually slight advantage to just-in-time compilation. That means that it can achieve higher performance than you can get from a static compiler like you get with Swift and LLVM. Now, better performance, that sounds good. It does have a trade-off like everything in this world, which is that it needs more memory because it has to run this compilation in memory at runtime. And secondly, it has the disadvantage that because it has to compile it at runtime, your initial performance isn't as good. over time, its performance gets better. So its out-of-the-box performance, as it's called, is not as good as you get from ahead-of-time compilation from something like Swift. But for very long-running applications, just-in-time compilation tends to be good, which is why, interestingly, there are a couple of people looking at adding just-in-time compilation to Swift. So to allow that intermediate representation to be converted to machine code at runtime for Swift rather than ahead of time.
Dice.com will help you accelerate your tech career. Whether you're actively looking for a job or need insights to grow in your role, Dice has the resources that you need. Dice's mobile app is the easiest and fastest way to get ahead. Search thousands of jobs from top companies. Discover your market value based on your unique skill set. Uncover new opportunities with Dice's new career pathing tool, which can give you insights about the best types of roles to transition to. Dice will even suggest the new skills that you'll need to make the move. Manage your tech career and download the Dice Careers app on Android or iOS today. And to check out the Dice website and support Software Engineering Daily, go to dice.com/SEDaily. Thanks to Dice for being a continued sponsor of Software Engineering Daily. And if you want to support the show and check out some new career opportunities, go to dice.com/SEDaily. You're talking about some performance benefits of Swift, and certainly those performance benefits are relevant to the popularity of Swift. Swift has quickly become one of the most popular languages around. In 2015, it won first place in Stack Overflow's Top Languages survey. In 2016, it won second place. Performance is not the only reason that people love Swift. There are a number of developer ergonomic aspects of Swift that people love. What are some of those features? I know you mentioned one earlier in terms of the avoidance of null pointer exceptions. What are some of the other ones?
Yeah, so optionals is a good example. Another one that you can do is, so let's say you're writing a function, and that function returns a value. So you're just doing, some kind of simple check to see whether something is on or off, and you expect it to return true or false. Now, in Java, if you called that function but didn't actually do anything to pick up the return value, Java will compile it, and that's fine as far as it's concerned, right? You called a function, ignored its return, and that's okay in Java terms. Now, in Swift, the compiler actually gives you a warning. It says, you called a function which returns a value, and you didn't actually pick up that value. Right? So that's a compiler warning which helps you understand you probably should have done something with that return value. So it's another way in which it's trying to help the developer not make mistakes and insert bugs into their code. Now, obviously, maybe you intentionally only have a return value as something that you may want to know, but you don't have to know. So they also allow you to mark that function as having a discardable result. So you just add an annotation to the function as the function writer as at discardable result, and then people using that function don't have to do anything with the return. If you don't mark it as discardable and they don't do anything with return, then they get a compiler warning to say you've probably just inserted a bug into your code. And there's many, many more like that. One of the really cool things about Swift is there's something called Swift Evolution, which is both a mailing list and a mechanism so that anybody can actually raise a suggested change to the language. So this is enabling the community of developers to actually say, have you thought about doing X as a way of making programmers' life easier? So that tends to be fairly unique. Most of the languages I've worked with in the past, There's a core team of people that decide what the language should look like, and they implement features, and as a developer, you just get it. Whereas with Swift, they're taking this approach of saying, well, let's ask the people who have to write Swift code what they think would be useful to have in the language and how things should change. And even stuff that comes from the Apple core team working on the language goes through Swift evolution. So they propose the code change to a programming style, and the community, so anybody that wants to sign up to the mailing list or go and look at the GitHub repo, can comment on whether they think that's a good or a bad idea or how it would affect them. So I think that's kind of unique, and it's actually like a really, really neat improvement to help build a language that developers actually want to use by having the developers provide their input on what they want it to be.
Swift has been used on client devices for several years now. Many of the iPhone apps that I use are written in Swift. Why should developers build server-side apps with Swift?
So there's a number of reasons, but the first of them, let's say you are one of those developers building an iOS or a watchOS or a macOS app. So you're building an application for an iPhone, and there's a good chance that that application needs to have some kind of data store or functionality which you need to have off the device. Right? There's many examples of this. Let's say you're building a to-do list, and you want to be able to save that so that you can access it from your laptop as well as from your phone. I don't know, you've got a game and you're trying to store high scores so you can compare them to other people. So to have that, you need something off the device. So you need some kind of backend server, and that server will work with a database or could work with many other things. Now, the advantage of having Swift on the server is that I, as the developer for the iPhone app, I can also write that server piece, which is going to take the data and store it in a database. So that means I don't have to learn two programming languages, or I don't have to work with another team. I can do both parts of that myself. So that's really kind of like the first reason why it's kind of interesting purely to developers. Some of the other reasons why Swift on the server is interesting is, back to those characteristics of being fast. Actually not requiring a lot of memory is quite an advantage, and that comes from being a language designed to be running on a device. It's very, very low memory footprint. It doesn't take a lot of RAM in which to run that server application, and those same features as being expressive and safe means that it's an interesting language to be using on the server as well.
If we're talking about the other languages that people might be using on the server, those are Java, NodeJS, Ruby, primarily maybe Python. All of these languages have some of the developer ergonomics of Swift, though Swift was created later, so it's safe to assume that with Swift, these were built in from a more fundamental point of view. They were not, I don't want to call them bolt-ons, but, Java 8, it was not until Java 8 that this emphasis on functional programming entered the language. We could talk about those, but I guess let's focus on performance, because I know that, Java is the performant of the three between Java, Node.js, and Ruby. Java is the most performant. I know a lot of Ruby shops end up making their applications in JRuby. They start with a Node app, or they start with a Rails app, and then when they get to a point where they need the performance of Java, they build their Ruby app to compile to Java, or to compile to Java bytecode. I don't remember exactly how it works. How do these other languages compare to Swift on performance?
Yeah, so that's one of the areas where Swift comes out pretty well, and some of it is down to fundamental characteristics. So Swift, like Java, is a typed language. And what that means is when I declare a variable or a constant, right? So I declare a thing. I declare what type it is. So I say this thing is an int, or it's a long, or it's a string, or it's a hash map. Right? So I have to state exactly what it is. Now, that's true of languages like Java. It's true of languages like Swift, but also for things like C. The other end of the scale is something like JavaScript, whether that's in the browser or on the server in Node.js. So when you write JavaScript code, you just say it's a variable, and you don't actually give any information about what type that is. And the side effect of that is when I create a var in JavaScript, it can store an int or a long. It could store a string. In fact, it can actually be a function. So that makes it somewhat easier to program. I just keep declaring vars. I don't have to think ahead of time about what's going to be stored in it. So it actually makes it slightly quicker to develop. But the downside is when we compile that code, so once we actually have to compile that down to machine code and assembler instructions, the challenge is knowing what the things are. So in Swift and in Java, because I've declared, say, two values is an int, and I put a plus sign between them, so I want to do the plus operator. What will happen is Java and Swift will both go, okay, those are two ints, and you want me to add them together? That's a single assembler instruction. That's an add-I. So I can add the two together and return the value in a single instruction. Now, to do the same thing in an untyped language like JavaScript, where I got two vars, the first thing the compiler has to do is actually interrogate what's inside those vars to work out what type it is. Because if it is two ints, it's still going to use the add-I instruction, but it has to put a whole lot of effort in place to understand that var A happened to be an int and not a function or a string, and var B happened to be an int and not a function or a string. So having languages which are typed means that they execute much faster at runtime because it's easier for the compiler to know what it does and to create the minimum number of assembler instructions to execute it. So that means typed languages like Java and Swift are much, much faster than untyped languages like JavaScript and Ruby and so on.
I saw you give a presentation where you were discussing the importance of not just Swift's high performance, but also the fact that it has a small memory footprint. And this is particularly important, as you mentioned in this talk that I saw, in the time of cloud computing, especially today where we're getting closer and closer fit between the size of our programs and the size of the virtual machines or containers that we're renting out from cloud service providers. How important is the small size of Swift's memory footprint to somebody who is developing a server-side application that they're going to be deploying to the cloud?
The interesting thing there is, so anybody that wants to deploy an application to the cloud will soon start to understand that you have to deploy it into some kind of container. So you're kind of renting a virtual machine, a virtual bit of hardware that your application is going to run in. And it pretty much doesn't matter which cloud provider you go to. They charge you an amount of money according to how much memory that container needs. So, for example, in Amazon, if I wanted a nano instance, I get charged something like $5 a month for 512 megs worth of memory. If I want 1 gig's worth of memory, then I get charged twice that. If I want 2 gigs worth of memory, then it doubles again. So the amount that they charge you is actually based on the amount of memory that you want to use. And usually for clouds, you actually have to grow to quite a large container before it starts giving you more CPU. So basically the charge rate is done by memory, not by processing power as such. So the smaller your application is, the less memory it's needed, the cheaper it is for you to run in the cloud. So running something like Swift actually uses less than half the memory of running something like Java. And that means that if I have a large server application which has to run many instances in order to deal with tens of thousands of users, if I'd written it in Swift, it would cost me half as much in terms of hosting costs in the cloud as it would if I'd done it in Java. So there's this kind of new breed of economics of running an application based on the cloud, which has gone from how many CPUs does my machine have, because it's the CPU that determines how much processing I can do. In the cloud, you get charged by memory, and the amount of CPU you get kind of comes for free with that. So if I can build a server application that uses half the memory, it costs me half as much to run it.
This is slightly off topic, but how much of an application, of a typical application's cost is network I/O? Because I think they also charge you based on network I/O, right? It's not just the memory footprint.
They do, yes. But if you consider that the amount of network I/O you've got basically depends how many users you have, not what language you happen to be receiving the requests or responding to the requests in.
Right.
So if you're building server applications which are using a REST API, then that traffic is based on the number of users. So that's kind of a fixed cost regardless which language you implement the server in. But yes, I mean, that is a factor for running the application. But the hosting cost itself is dictated almost entirely on the amount of memory that you're using.
Okay, sure. Yeah, okay. So that's the highest order bit, basically, is the size of the memory size, memory footprint.
Yeah.
Okay, great. I need to do a show about cloud economics. So isomorphic development is this term that's used to describe development where the language is the same on both the client and the server. I think it goes without saying that isomorphic development is desirable. We would rather have, all things being equal, the same language on the client and the server so people can move fluidly between client and server. We don't have silos in terms of language understanding. And one valuable aspect of isomorphic development is that you can actually choose to execute code on either the client or the server, depending on how much available resource the client has. I mean, this is not going to be true for every aspect of an application, but there are certain portions of the code that could execute on the client or the server. And I've seen you talk about this when you're discussing isomorphic development in Swift. And it got me thinking, because I don't know much about this isomorphic development pattern. Are there libraries for intelligently managing how much code executes on either the client or the server, or do you deploy the code to both the client and the server, and you have some kind of flag that you turn on or off depending on how much battery life is available on the phone, or how much, what version of the phone it is? How do you manage that type of isomorphic development where you have code that can execute either on the client or the server? How do you manage that intelligently?
I'm not aware of any framework that does it intelligently today, and it would probably be an interesting thing for someone or a startup to actually produce. But
it'd be useful.
There's some kind of classic use cases for it, certainly in iOS development in Swift. So the first one is going to be your obvious. So you've got users who are complaining about how quickly the application drains memory. And it's because you're doing, these huge computational tasks inside the device, which could be offloaded to the server. So in that case, one of the easy things you can do is just say, okay, I'm going to release an update of the app that actually does the processing of this thing in the server rather than the client now. So it makes a request of the server and gets the results back, and the server's actually going to do that big computational task, which would use a lot of battery if it was on the device. So you've got that idea of being able to drag code around based on testing, whether that's testing you did ahead of a release or based on user feedback. Another way of looking at it is offline mode, right? When you're developing stuff for a phone, there's a good chance that you've got function that you want to be able to use offline as well as online. So you could run the app such that if you are offline, there's a certain set of capabilities that we can execute on the device. But if you do have a network connection, then we can have the server do that instead. And you're using exactly the same code in both places. So we're just offloading it to the server because network is available and it's best done on the server because of, maybe battery reasons, maybe data it can access, maybe it can get updates from another service. But for offline mode, you have to have some of that function available locally. Now, if your backend was written in a different language, then you'd have to implement the same function twice. If you've got the same language in both places, not only are you being able to do both parts with one development team, you're reusing code between both parts.
For engineers that are building in the Apple ecosystem, Swift on the server gives them this integrated developer experience. And when I was researching for the show, I found plenty of people who were like, oh, Swift on the server is great. I don't have to write my server-side code in NodeJS anymore. Although this is the same reason that people choose React Native together with Node.js. Or, I mean, if we're not talking about the Apple ecosystem, people choose Node.js together with some front-end JavaScript framework. I think this was the thrust of what made Node so popular in the first place, was people were saying, oh my gosh, I have to write a JavaScript front-end app and a Java backend or a Rails backend or a Python backend. And people didn't like doing that as much as they did doing everything in JavaScript. So for people who take seriously the premise of React Native, by the way, React Native, for people who don't know, is essentially a way of reusing web components that you create, not web components, but they are components, React components that you build on the web. You can reuse them in your iOS app so that you don't have to rewrite every piece of code, because a lot of mobile apps, their mobile app looks like the desktop app, or it has a similar experience, has similar components. This is like a pretty common pattern. And so people can choose to do React Native, where they have these components that are in a JavaScript-like thing or I think they're in React. They're in something that looks like React. I don't remember exactly what it is, but it interweaves with their iOS code, and there's some compilation step where the React Native component gets turned into Swift code, or I think, or maybe it just gets rendered. I should refresh my memory on this. But the thrust of my question is, for people who can choose between these two full stack paradigms, and I think that this is probably kind of a goofy question to ask, because I think people basically, they either evolve in the Swift ecosystem and the full stack Swift makes sense to them, or they evolve in the JavaScript ecosystem and full stack JavaScript makes sense to them. But let's just say, like, a hypothetical person who could do either one, what kinds of applications would make sense for full stack Swift, and which ones would make sense for full stack JavaScript?
The first part there is, so this whole concept of isomorphic development, right? Reusing code front end and back end. It's not new, and it's one of the reasons why Node.js is so popular, working with the browser. So JavaScript and Node.js is kind of one of the big areas where isomorphic has taken off, and it's been of huge interest. Now, that does lead to an argument that, yes, with things like React Native, you could just use JavaScript to create React Native apps on all of your front ends, right? If we consider our front ends currently to be web, iOS, and Android as the major players. Now, whilst that would work, there's some thought leadership being done by a group called ThoughtWorks. And they kind of first implemented this at SoundCloud. They started talking about the concept of something called the BFF, the backend.
I did a show on this.
Okay.
I did a show on BFF with Lucas Plotnicki, who worked with SoundCloud on that ThoughtWorks project.
Yeah. So I mean, the key conclusion that they came to is, mobile and web front ends have different requirements, and they therefore have different requirements of the back end. So your backend for web needs to do different things to your backend for mobile. So under that paradigm, it makes sense to have JavaScript and Node.js as the backend for web. But if you've got to have a separate backend for mobile already, then what would that be depending on what your front-end mobile implementation is? Now, so that you've got this sense of language pairing, but the other thing that came out of the backend for front-end model was around having self-contained agile teams. So it's the fact that not only do you have different requirements for the backend for web than you do for mobile, you probably have different timescales on which you want to be able to deliver function. So let's say there's the new release of iOS that's just come out. There's some new function that you want to be able to exploit. So that means you need to deliver a new version of your mobile app, and you may well need to provide a new version of the backend for it because it needs to access something new from a service. So you want to be able to build that and deliver it as quickly as possible. Now, that means that if you have a single backend, you're actually tied to the backend delivery schedule because they have to worry about other front ends and potentially disabling those other front ends by changing the backend. Now, the reverse is true for mobile clients. So if you're using something like React Native and you're using basically the same code base across all of your mobile front ends, and a new version of iOS comes out and you want to exploit that new function, you can't just add the code and deliver it for iOS because you're potentially affecting your Android deliverable as well. Now, you could release the iOS code without releasing the Android version, but you have changed that same code base. So you've added a level of risk and a level of retest that needs to be done to make sure you don't affect the Android implementation. So under this back-end for front-end pattern, you actually want to get to the point where you have a separate Android team, a separate iOS team, and a separate web team, and that they own both their front end and their back end, and so that they can deliver on their own schedule for their own customers, their own users' needs, and for the feature and function that's available to them. And then that becomes best to do in the same language, front end and back end. Now, with things like React Native, yes, you can do the same stuff across both platforms, and some of the integration with the device is actually pretty good. But you still end up with this, the look and feel for an iOS app is generally different to what it is for an Android app. And if you're doing things consistently because you're using React Native, then you either start to have toggles in there to do different things differently on Android and iOS, or you actually end up with two different apps, at which point you might as well be doing them in Swift for iOS and in Java for Android. So generally this concept of wanting to develop features for your users, deliver them on your own schedule, and wanting to be self-contained and agile and not have a knock-on impact to the teams delivering for Android and for web means it does make sense to separate things out into separate projects, and then it becomes more obvious that doing it in the native language for each of those three makes sense. So you end up with a Swift application on iOS with a Swift backend. You end up with a Java implemented Android app with a Java backend, or maybe Kotlin for those two, and for web, obviously JavaScript and Node.js on the backend.
Okay, yeah, that's. I could also just see the more simplistic world, like let's say you have a startup and you say, you know what, our mobile customers are the people we need to focus on the most, and we've got limited developer resources. We're going to focus on the Swift iOS app, and because that is our main focus, we're going to put Swift on the server. The web platform is going to be an afterthought, and maybe we have one guy or one girl that works on the web platform, and we have non-isomorphic development there. And then maybe you get Swift maybe you get some Swift-like thing that compiles to JavaScript later on. I wouldn't be surprised if that happened. Then you could have a more simple isomorphic development world. But anyway, you've convinced us that Swift on the server makes sense in some contexts. Maybe not every context, but at least in some contexts. And you've also said that when Apple announced Swift, it was just for client devices. The other thing is that it was closed source. In 2015, Apple open sourced it. So why was it important that Apple open sourced it? Why was this an important point in the timeline towards getting Swift on the server to work?
Yeah, so Swift as an open source project was announced at the start of December 2015. And actually the day after that was the day I started working on Swift. And part of that was, so whilst part of the open source announcement said Swift is now available on Linux, and that was certainly true, it was just very, very limited. So you had the ability to write and execute Swift code on Linux, but there was no, should we say, API ecosystem. So some of the core libraries for Swift just did not exist on Linux. So the concurrency library, the thing that lets you run your code over multiple CPUs, which is called Grand Central Dispatch, that didn't even compile on Linux on the day Swift was open sourced. The kind of the main library that people are used to using called Foundation. So it compiled, but I think only about a third of the APIs were actually implemented. So you could write Swift code and you could run it, but the APIs that actually let you do meaningful tasks really weren't there. And by open sourcing it, it's actually allowed the community and people who are interested in making Swift successful on non-Apple ecosystem platforms, they could actually help to make it ready. So one of the first things I started working on was Grand Central Dispatch, getting this concurrency library working because, servers are multi-CPU, and if you want to deal with, large numbers of concurrent connections, you need multi-CPU exploitation. So I think it's fair to say that if Swift wasn't open sourced, then Dispatch would not be available on Linux today, and I don't think a lot of the work that's been done in Foundation would have happened. And that's not to say that Apple doesn't care about Linux. It's more a case of there's a limited number of employees which can work on this stuff, and by opening up to the community, it enables a huge number of people who think Swift on the server or Swift on Linux is going to be valuable to take part and to actually put something in to get something back from this. And I think that's one of the reasons why in the first 6 months of being open source, there was something like 12 different server-side frameworks that sprung up.
For more than 30 years, DNS has been one of the fundamental protocols of the internet. Yet, despite its accepted importance, it has never quite gotten the due that it deserves. But today's dynamic applications, hybrid clouds, and volatile internet demand that you rethink the strategic value and importance of your DNS choices. Oracle Dyn provides DNS that is as dynamic and intelligent as your applications. Dyn DNS gets your users to the right cloud service, the right CDN, or the right data center, using intelligent response to steer traffic based on business policies, as well as real-time internet conditions, like the security and the performance of the network path. Dyn maps all internet pathways every 24 seconds via more than 500 million trace routes. This is the equivalent of 7 light years of distance, or 1.7 billion times around the circumference of the Earth. With over 10 years of experience supporting the likes of Netflix, Twitter, Zappos, Etsy, and Salesforce, Dyn can scale to meet the demand of the largest web applications. Get started with a free 30-day trial for your application by going to dyn.com/sedaily. That's dyn.com/sedaily. After the free trial, Dyn's developer plans start at just $7 a month for world-class DNS. Rethink DNS. Go to dyn.com/sedaily to learn more and get your free trial of Dyn DNS. When you say that Swift was open sourced, does that mean that the compiler was open sourced?
Every single part of it has been open sourced. So it's built on LLVM, which was always an open source project. Swift, the language and the compiler itself, that's been open sourced.
When you say the language is open sourced, so I guess I don't understand what that means, because people could when Apple first announced it, when it was quote unquote closed source, people could still write applications with Swift, right?
So what this means is if I wanted to actually modify the programming language itself, then there's a process to do that through open source. I can download its source code, I can modify it, and I can send that back with a request to get it integrated.
So, but the source code for a language, that's essentially the compiler, right?
Yes. Yeah. I mean, for Swift, you are basically talking the compiler, which parses the Swift code that we've defined down to the intermediate language, and then compiles that down to machine assembler.
Right. Okay. Just wanted to clarify that, because I was like, when Swift was announced, it was closed source, but people could still write code with it, so the documentation was there. But it's just that you didn't know what was going on between the Swift code you wrote and the machine code that executed on your box.
That's correct. But I mean, as part of the open sourcing, they also open sourced a lot of the core libraries. So Foundation became open source. Dispatch, or Grand Central Dispatch, the concurrency library, that was open sourced. Swift Package Manager, their way of doing build and dependency management, that's open sourced. The test framework is open sourced. So really all of the core capabilities are there for people to actively contribute to.
So as you mentioned, you've been working on Kitura, which is the Swift web framework that IBM is building, and there's a bunch of other Swift web frameworks. A web framework allows people to build web applications to run Swift on the server. And as you're talking about building this concurrency library, it sounds so interesting and so exciting, because I've done a bunch of shows recently about scheduling, and scheduling in terms of, you've got, 15 MapReduce jobs, and you've got a bunch of different machines sitting on your cloud provider that are assigned to you, and you can allocate those jobs to those different servers however you want to. And that's a hard problem. It's not a solved problem. It's everybody writes custom schedulers in order to do it. And you're talking about writing a scheduler for threads at a low level, and I imagine that the problems and the subjective challenges you have are just as interesting, just as debatable as these things that occur at the higher level. Is that accurate?
Yes. I mean, implementing good concurrency libraries is not an easy task. For Swift and Dispatch, so we've got the advantage that it was implemented by the team in Apple who've been working on Dispatch for a number of years. The problem is that it didn't work on Linux. So our first problem was really more porting something which already existed to a different platform. And the other advantage is that a couple of my colleagues, Hubertus Franke and Dave Grove, they have a very long history of working inside the Linux kernel and on runtimes. And they've been working on this for the last year or so to really not just make it work on Linux, but to do some of that really low-level scheduling kind of stuff to make sure that it will take work and dispatch it over all available CPUs and actually scale to almost 100% CPU usage under high load. And that's the goal of concurrency library, is to make sure that any work that you want to do can be distributed over all of the available CPU resource and therefore executed as quickly as possible.
You have spent 15 years of your career building Java applications, as we mentioned. That is most of the time that Java has been around. And from what I hear you say, and in the presentation I watched of you, you seem to believe that Swift has a real chance at becoming the enterprise development language that supplants Java, or at least is another one that can rival Java in terms of its size, in terms of its penetration, in terms of its usefulness and performance. What's your prediction for how that's going to proceed, how that rollout is going to proceed? And I don't know, do you have any interesting predictions?
So Java's been around for something like 23 years now, and I don't see it as going away in the same way that some of the older languages which people consider to be now redundant, like COBOL, a huge amount of infrastructure like ATMs, the backing infrastructure for that is still running on COBOL, and COBOL is still going strong. So I don't think Java is ever going to go away. I think that there's a whole load of workloads which you do in Java today that you'll potentially be able to do on Swift in the future if you want to. I think the fact that it's a typed language like Java means that it's got the potential for performance. The fact that it's typed also means that you're less likely to have problems and bugs that just appear at runtime where you have calculation problems, and that means it's got potential for doing transactions and that sort of thing. So it's got potential to cover a lot of the use cases that Java has today. So I think we'll see Swift growing over time, and I think you'll see it being applied to many, many more use cases in the same way that Java can be used in almost any scenario. But I don't think Java's going to go away. I think it's going to be there for a very long time, and Java will continue to evolve. As you said, Java 8 brought in some new stuff. It brought in lambdas, so the ability to pass around functions, and it had more functional programming constructs added. So I think Java's going to continue to evolve, and it will continue to be a huge programming language, but I believe there's a lot of scope for Swift to grow, particularly for cloud deployments. And I think another interesting place is going to be around Internet of Things, because it's small, and it's already been designed to run on an embedded device. So there are many, many more embedded devices that it's a good language for.
Fascinating. Yeah, and I mean, as far as like Java going away, like I think about all of the Hadoop technologies and how closely tied with the JVM ecosystem they are right now. I mean, there's some work on interoperability with other languages going on, but just taking the Hadoop ecosystem, if you looked at like, okay, what if I spin up an enterprise today? Okay, maybe I do a lot of the business logic in Swift, like the transactional logic or just server-side stuff. But if I get enough data to build some big data stuff, then I'm going to need to work with Java. And but yeah, I could even imagine a polyglot world where you want Swift as part of your server-side business logic, and you want JVM stuff as the other server-side logic. Anyway, interesting. Okay, well, I think we've covered a lot of ground, Chris. It's been really interesting talking to you.
Yeah, no worries. Thanks for inviting me and giving me the opportunity to chat.
Yeah, for sure. And maybe if there's some developments in the future that you want to shed more light on, I'd be happy to have you back on.
Yeah, I'd love to, and I think there's going to be many more things in the future to talk about as Swift evolves and starts getting used in many, many more different ways.
Wonderful. Thanks to Symphono for sponsoring Software Engineering Daily. Symphono is a custom engineering shop where senior engineers tackle big tech challenges while learning from each other. Check it out at symphono.com/sedaily. That's symphono.com/sedaily. Thanks again to Symphono for being a sponsor of Software Engineering Daily for almost a year now. Your continued support allows us to deliver this content to the listeners on a regular basis.
Wow!